This video is about drawing stack diagrams, which are a way to visualize what's going on in memory while a program is running. Stack diagrams show us much of the same information that we can get from the debugger, either at the command line or within VS Code, because they keep track of the functions that are executing and the local variables in each of those functions. But often it can be useful to draw this by hand to show what we expect to be happening based on the code that we have written. And stack diagrams will also help us to illustrate a number of concepts related to pointers, dynamic memory, assembly code, and more over the course of the semester. So let's head over to the whiteboard and draw some stack diagrams. I have here a couple of C programs that should look familiar from our in-class activities. One that computes the floor of log base 3 of 10, and one that finds the last box that the hamster is going to eat a peanut from. So let's trace through the execution of these programs and use a stack diagram to keep track of what's going on. When we run a C program, we know that execution begins from the start of the main function. And whenever we have a function executing in our C program, there is a chunk of memory associated with that function to store its local variables. So when we begin the main function, we should draw a box on our stack diagram to store all of the local variables for main. In the main function, we have three local variables, x, b, and y, and so there will be some place in memory within the stack frame of the main function that stores the values for each of those variables. At the beginning of the function, the locations for these variables exist, but they have not yet been assigned a value. But once we start executing the code in main, we will assign the value 10 into x and 3 into b, so we'll fill in those values in main's stack frame within our stack diagram. When we get to this line of our C code, we know that it will eventually fill in a value for y, but to compute that value, it is calling a function log floor. And we know that when we call a function, the execution of main is paused while that function does its work, and then when that function returns, main will resume its execution using the return value it got back. So main is paused on this line until it gets back a return value from log floor, and when we call a new function, we get a new frame on top of the stack to store all of the local variables of that function. So we add another box to our stack diagram and label it as belonging to the log floor function. And that function has three variables, the two inputs that were passed in, and the local variable exponent. And when this function is called, we give it the values of x and b, so those values are immediately copied into the stack frame for log floor. The value of x becomes the value of input, and the value of b becomes the value of base. Now we can start to trace through the log floor function. On the first line, we assign 0 into our exponent variable. Then we check the while condition, and since input is greater than or equal to base, we go into the while loop, where we will add 1 to the exponent and divide input by base, storing the result back into input. So when we divide 10 by 3 and throw away the remainder, we get 3, and we store that result back into input, so this value gets updated to 3. Then we go back to the top and check the loop condition. Input is still greater than or equal to base, so we execute the loop again, incrementing exponent and dividing input by base. And now when we go back to check the loop condition, input is no longer greater than or equal to the base. So we jump over the body of the loop and arrive at the return statement. So if we paused the execution of the program before this return statement, this would be the current state of all of the local variables, both in main and in the log floor function. But if we continue executing from here, log floor is going to return the value of exponent, and when a function returns, the stack memory used to store its local variables is deallocated. When we get back to main, log floor has returned the value 2, and so this expression now evaluates to 2, and the value that we store in the variable y when main picks up where it left off is now 2. After which we continue with the print statement, and this means we are calling the function printf. So we would then get a new stack frame for the printf function, but I will not ask you to draw stack diagrams of built-in C library functions. And the program will finish by printing that the floor of log base 3 of 10 is 2. Next, let's look at a slightly more involved example where our hamster is eating peanuts from the fullest box. Again, the program starts executing from the beginning of main. So at the bottom of our stack diagram, we will have a box indicating the stack frame for main. In that stack frame, we have a few local variables for peanut counts and last box. The last box variable stores an integer, much like the variables we had before, so we'll draw it in the same way. But the peanut counts variable refers to an array that stores 2 integers. And when we declare an array variable in C, that allocates a contiguous chunk of memory to store the appropriate number of values. In this case, we'll get 2 consecutive boxes that hold integers. When we execute the first line of main, we set the values in this array to 5 and 6. And again, to get the value of last box, we're going to have to wait until a function call returns. So for now, we will leave this box on our stack diagram blank, and we will add a stack frame for the function that we are calling. In the getLastBox function, we have 4 local variables. The inputs, peanut counts, numBoxes, and amount, along with the variable maxBox that we declared in the body. A couple of things to note about the variables in getLastBox. One is that we have variables called peanut counts in main and in this function, but those are different variables that are located in different places in memory. And this corresponds to the idea that a local variable in a function is different from a local variable in another function. Those are separate scopes, and they refer to different locations in memory. We can fill in the values for numBoxes and amount based on the parameters that were passed into the function. Their initial values are both 2. But when we passed in peanut counts, something slightly different happens. In particular, when we pass an array variable into a function in C, we don't copy the entire array. What happens instead is that in the function, we have a pointer back to the array that already exists. We draw that by an arrow from the variable here to the start of the array that was passed in. We'll talk more about what this pointer means in the next video, but we'll also see a consequence of the pointer in a moment when we start operating on the values in the array. The first line of the function sets maxBox to 0, and then we check the while condition. Amount is greater than 0, so we enter the loop, and we will update the value of maxBox based on what we get back from the argmax function, which means that the getLastBox function is now paused on this line, waiting for a value to come back from the argmax function. And when we call argmax, we get a new frame on top of our stack to store all of its local variables. In this stack frame, we have 4 variables: the arguments, array, and length, plus the local variables max index and I. We got the input array from the peanut counts variable in getLastBox, which means that array should point to the same place that the peanut counts variable was pointing. And we got length from numBoxes, so its value is 2. Then we set max index to 0. The for loop initializes I to have the value 1, then checks the loop condition. Since I is less than length, we go into the body of the loop, and we check whether array at max index is greater than array at I. Array refers to the peanut counts array from main, and so array at max index, well, max index is currently 0, so that refers to the value 5, and array at I is 1, so this refers to the value in bucket 1, which is 6. So 5 is less than 6, and we see a bug in my code. We want to update in the case where the ith element is bigger than our previous max, so this should be a less than sign. And since 5 is less than 6, we will go into this if statement, and that will update the value of max index, copying the value from I. Now we've reached the bottom of the loop, so we go back to the top and perform the increment operation. And now that I is 2, when we compare is I less than length, that is no longer true, so we'll skip over the body of the loop and arrive at the return statement. So now we have a stack diagram as of the first time that the execution in the program reached this return statement. So if we had used the debugger and put a breakpoint on this line, and then used the where command, we should see that there are 3 different functions currently on the call stack. And if we asked the debugger to print out all of the local variables of those functions, we should see these values that we have tracked. If we continue executing from this point, peanuts will return the value in max index, so it is returning a 1 back to getLastBox, and that return value is being stored into the maxBox variable. In addition, when this function returns, the memory that was holding its local variables gets deallocated, so that stack frame goes away and we erase it from our diagram. And we pick up the execution of lastBox from where we left off, saving the value 1 and proceeding to decrement peanut counts at that box and decrement amount. When we decrement peanut counts of 1, that is going to change the value that is stored in this array. So we now update element 1 of that array, decrementing its value from 6 to 5. We also decrement amount, and then we return to the top of the while loop, check the condition. Amount is still bigger than 0, so we go back into the loop and call argmax again. When we do that, we get a new stack frame, and this new stack frame overwrites the memory that was previously in use for the earlier call to argmax. Since we're calling the same function again, we'll end up with the same names for all of the local variables. But it's possible that on this new call to the function, we might have passed in different values for those variables, and so we need to keep careful track in our stack diagram of what values are currently stored in each of them. In this case, array still points to the same place, and length is still 2. We'll set max index to 0, and initialize I to 1. Since I is less than length, we'll go into the loop and check our if condition, comparing array at max index, which is 0, to array at I, which is 1. So array at index 0 stores the value 5, whereas array at index 1 also stores the value 5. So this less than is not true, and we will skip over the if statement, returning to the top of the loop and performing the update, which increments I to 2, at which point the condition is no longer true, so we drop to the bottom and return. This time we are returning a value of 0 for the max index, and when getLastBox returns, that return value will get stored in the maxBox variable, so its value is now 0. Once again, returning from the function eliminates its stack frame. And when we resume executing getLastBox, we decrement peanut counts at 0, which updates this entry in the array from main, and we decrement amount to 0. Now we've reached the bottom of the loop, so we go back up and check the condition. Since amount is no longer greater than 0, this is false, and we drop down to the bottom where our return statement gives back maxBox. And so when getLastBox returns 0, we fill that into our lastBox variable in main. Again, the stack frame goes away, and main resumes executing right where it left off, and it will print that the hamster ends on box 0. I'd like to show you one more stack diagram to illustrate the operation of a recursive function, and for that we'll trace through my solution to the in-class bonus exercise that was about computing a greatest common divisor. Here we have a recursive implementation in C of Euclid's algorithm for computing greatest common divisors. The GCD of A and B is the largest integer that divides both, and the algorithm relies on the fact that GCD is preserved by the mod operator. But the important point right now is that this function calls itself. So let's take a look at what that looks like on a stack diagram. As always, the program begins with main, so we have a stack frame for main on the bottom of our diagram, and we initialize x to 24 and y to 45. At this point, main calls GCD, so its execution is paused, waiting for a return value. And we get a stack frame for the GCD function, which has local variables a, b, and d. we pass in x and y, so 24 gets copied into A, and 45 gets copied into B. Then we check if B is 0, and it's not, so we go to the else case, where we set A to be equal to A mod B. The mod operator gives us the remainder when we divide A by B. So when we divide 24 by 45, we get 0, remainder 24. So this just assigns the value 24 back into A. But now we call GCD again, which means that we get a new stack frame for this new function call. So our first call to GCD is paused on this line, waiting for the return value from the recursive call. And here we are passing in B as the first argument, so the value of B gets copied into the first input, which is A, and the value of A, 24, gets copied into the second input, so in this call B is 24. B is still not equal to 0, so we go to the else case and we set A equal to A mod B. And now when we do 45 divided by 24, we get 1, remainder 21. So the mod evaluates to 21, and that value gets stored back into the A variable. Now we arrive at this line again, and we again recursively call GCD, which means we need a new stack frame. So this call to GCD is also paused on this line, waiting for a return value from the recursion, and it passes in the value of B for the first argument, so we get 24 for A, and the value of A, 21, goes into B. As we execute the body, B is still not 0, so we go to the else. We set A equal to A mod B. So when we divide 24 by 21, we get 1, remainder 3. And now we get to this line where we again recursively call GCD. This call to GCD receives 21 as its first argument and 3 as its second. The condition is false, so we go to the else. We compute A mod B, and when we divide 21 by 3, we get 7 remainder 0. So the remainder 0 gets stored in A. And now again, we make a recursive call and get another stack frame for GCD. And this time, we pass in 3 for the first argument and 0 for the second. So when we check if B is 0, that now evaluates to true, and we assign D the value from A. Now that we've executed the if, we jump over the else and arrive at the return statement, and we return the value of D. So 3 gets returned, and the orange call to GCD, which was paused on this line, now gets back the value 3 and stores it in the variable D. At the same time, when GCD returned, its stack frame went away, so we lose this topmost box. But now the orange GCD call resumes executing, and it's hit the bottom of the else case, so it goes on to return the value of D. That eliminates this stack frame and brings us back to where this GCD call was paused. It gets back a return value of 3 and stores it in its local variable D. And this proceeds all the way down the stack. This call will now return and give back the value 3, which will be stored in this D variable. And then that GCD will continue executing, hit the return statement, return a 3, and have its stack frame deallocated. Then this very first call to GCD resumes executing, stores the value in its variable D, and returns it, which finally brings us back to main, where this call has returned a value of 3, and that gets stored in the variable d, and now main can resume executing and print out the result. So if you're ever confused about what's going on in a recursive function, drawing a stack diagram can be a great way of keeping track of all of the different calls to that same code.